Continue our description of the solution of the Schrödinger equation for the hydrogen atom. We saw that there were indeed three quantum numbers as we would expect in 3 dimensions. One of them is associated with the confinement of the electron to within a distance r of the nucleus, and this is the quantum number that determines the final energy of the eigenstate, and it's called the principal quantum number. A second quantum number is associated with the allowed values of the total angular momentum squared. This is given the symbol L, and it's called the azimuthal quantum number. And then a third quantum number is associated with rotations in phi, and that is called M, or the magnetic quantum number. Now, n, just like in the one-dimensional problem, can take on integer values, and indeed it has an exact analogy to the particle-in-a-box solution. Phi is associated with eigenstates of the z angular momentum, and these are given by e to the I m phi. And so the rotation that this remain, the requirement that this function remain invariant on rotation around 360 degrees leads then to the constraint on m that it is equal to positive or negative integers. Finally, the constraints on L, which can be found from substitution into the Schrödinger equation, lead to the following conditions: that m lie between minus L and plus L, and that L itself be greater than 0 or equal to 0, but less than or equal to n minus 1. So let's compare this with the three-dimensional case, where for a free particle we had nx, ny, and nz all allowed to be an infinite series of integers. In 3 dimensions we have 3 quantum numbers: the principal quantum number n, which can be any integer, L, which can be 0 or less than or equal to n minus 1, and m, which can lie between plus and minus L. The eigen energies of the Schrödinger, of the hydrogen atom, depend simply on n, and have this form: me to the fourth on these constants times n squared. So they're very like 1 over n squared, and one way to remember this formula is just the ionization energy of the hydrogen atom, 13.6 electron volts, divided by n squared. The eigenfunctions are quite complicated. I've shown you here the first few eigenfunctions. Let's just sketch the very first one down. The constant at the front is just a normalization constant, but we see that the first eigenfunction looks like e to the minus r on a0. A0 is this quantity shown here, which when evaluated gives you the so-called radius, Bohr radius of the hydrogen atom. We've called it half an angstrom. It's actually 0.529 angstroms. So this is an exponentially decaying wave function away from the proton, and its 1 over e point occurs at about half an angstrom. The wave functions get more complicated as one goes to higher quantum numbers. Here the principal quantum number increasing. When we bring in L, we start to see a dependence on theta, and we bring in M, and we start to see a dependence on phi. What we're actually interested in is the probability of finding an electron, and now we have to remember that we are working in spherical coordinates. Because of that, we have to multiply any probability we calculate, it's the probability per unit volume of space, by the volume of space at a distance r. So as you see in this formula here, p at some distance r between the distance r and dr must be equal to the volume of that element of space, 4 pi r squared dr, times the square of the wave function, which is an internal function of r, theta, and phi. And here are what those probabilities look like in cross-section. They're spherically symmetric. So for here, the principal quantum number 1 and the azimuthal and magnetic quantum numbers 0, you see we have a shell which peaks actually right at the Bohr radius of the atom. In the case of the second principal quantum number, you see we now have an additional node in the distribution, but a main peak out at a larger distance. And now here, for the third principal quantum number, you see we have an additional node. For the n principal quantum states with L and M equals 0, there are spherical shells of probability for finding the electron. When we allow L and M to take on finite values, then the angular distribution matters. And I show you here an example of the allowed states for L equal 1. Remember that M can run between minus L and plus L, so this means that M can be plus 1, 0, or minus 1. There are 3 M quantum numbers for L equal to 1, and when one plots the eigenfunctions squared times 4 pi r squared dr, one gets these dumbbell-shaped probabilities lying along the x, y, and z axes. These are referred to as chemists by p orbitals. The orbitals associated with the principal quantum numbers, the spherical shells, are referred to as chemists by s orbitals. Only the principal quantum number matters in determining the energy of the hydrogen atom. And when you look at these p states, you might think, well, gee, that can't be true because a hydrogen atom could be in any one of these states. However, remember, these are probabilities, and one would make repeated observations of a hydrogen atom and stand an equal chance of seeing it in the plus 1, minus 1, or 0 state in a true spherical potential, and therefore, in fact, all the states do look equally distributed in probability, and the 2s and 2p states, 2 referring to the principal quantum number, the s referring to the fact that L is 0, p referring to the fact that L is 1, are degenerate in energy and, when measured repeatedly, symmetrically distributed.